Okay, imagine this. You're running a critical system, right? Maybe it's e-commerce handling millions of transactions, or maybe a high-stakes financial trading desk. And then, boom, two seemingly innocent actions happen at the exact same time, and suddenly your carefully kept data, inventory counts, whatever, it's just completely wrong.
Yeah, the classic race condition, nightmare stuff.
Exactly.
Yeah.
You've hit a race condition. And the real kicker, these bugs are just notoriously difficult to debug because they're non-deterministic.
Right. They only show up when the timing is perfectly unlucky. Maybe once a month, maybe never when you're actually looking.
It's maddening. And what makes it even worse is that, the weak isolation levels that most databases use by default, they just don't catch all these insidious problems.
Nope.
We're talking about subtle but really destructive things like right skew, where transactions basically make wrong assumptions.
Yeah, or phantoms, where data just seems to appear or disappear while your transaction is running.
Exactly. So developers are often left kind of stuck with no really good tools to detect or prevent them. How do we even begin to tackle this?
Well, you've really hit the nail on the head. This isn't some new problem. Researchers have been wrestling with concurrency since, like, the 1970s.
Like some decade.
And for just as long, their gold standard solution has been pretty clear: serializable isolation.
Serializable isolation.
Yeah. Its core promise is just incredibly powerful. Even if transactions run totally in parallel, the final result is exactly the same as if they had run one after another, serially.
Meaning no race conditions.
None. Zero. It prevents all possible race conditions.
Yeah.
Guaranteed.
Wow. Okay.
And this is the big question, right? Especially for system designers, for engineers going into interviews.
Yeah.
If serializable isolation is so great, why isn't everyone just using it all the time?
Yeah, that's the million-dollar question.
So that's kind of our mission today. We're going to dive deep into the three main techniques for actually achieving it. We'll look at how they perform, what the trade-offs are.
The stuff that really matters in an interview.
Exactly. This isn't just theory. It's about that nuanced understanding you need.
Absolutely. So, to get right into it, we've kind of zeroed in on three key strategies. First, we'll tackle what sounds simplest, but is surprisingly powerful. Literally just running transactions in serial order, one after another.
The single file line.
Then we'll dig into the long-standing champion, which is two-phase locking.
Yes, 2PL.
And we'll give a quick nod to optimistic concurrency control, but honestly, that's a whole other deep dive waiting to happen.
For sure.
Today, the goal is really about equipping you, our listener, with that practical, real-world context you need for your next technical interview.
Let's do it.
Okay, so it's almost counterintuitive, right? The simplest way to dodge all these concurrency headaches is just to get rid of the concurrency.
Pretty much. Actual serial execution. One transaction completes and the next one starts. Single thread.
It sounds almost too straightforward. But why did database designers only really start considering this feasible around, 2007? What changed?
Yeah, it really came down to two major shifts happening around then. First, RAM.
Random access memory.
Right, RAM just became incredibly cheap. Suddenly, for a lot of use cases, your entire active data set could just fit right there in memory.
Ah, okay. No more disk waits.
Exactly. When all the data a transaction needs is instantly accessible, you get rid of the biggest bottleneck, waiting for slow disk I/O, input-output. That made transactions way faster.
Makes sense. And the second shift.
Second was a better understanding of OLTP workloads.
Online transaction process.
Yep. Those transactions, they're typically very short, very quick, little bursts of work, and the long, heavy analytical queries, those are usually read-only anyway, and you can just run them separately, maybe on a consistent snapshot, using something like snapshot isolation. Keep them out of the main path.
Gotcha. So quick in-memory operations became the norm for OLTP.
Precisely. And you saw databases pop up that really leveraged this. VoltDB, HStore, Redis uses this model, Datomic. And what's really fascinating sometimes is that a system built for single-threaded execution can actually beat a complex multi-threaded system in terms of throughput.
Wow, that seems backwards.
Because it completely avoids all the overhead. No complex locking, no coordination messages flying back and forth, no context switching. It just processes transactions as fast as that single core can go.
That's a really key insight about single CPU performance. So for you listening, here's a classic interview question to think about. When would you choose serial execution over, say, two-phase locking or, 2PL? Think about those points we just made memory, short transactions.
Yeah, good one.
And I think a common anti-pattern, maybe a bit of a red flag in interviews, is when someone just dismisses serial execution, saying, oh, it can't scale.
Right. Too simplistic.
While, yes, single-threaded throughput is fundamentally limited by that one core, it's genuinely surprising how often that single CPU core can actually outperform more complex systems because it avoids all that locking mess. It's a real trade-off, isn't it?
It absolutely is. But, and this is a big but, there's a critical catch. If your application uses interactive transactions,
Meaning what, exactly?
meaning the app sends one command, waits, sends another, like it does a select, gets the result back over the network, thinks for a bit, then sends a new pdate.
Ah, okay. Lots of back and forth.
Yeah. In a serial execution model, that leads to absolutely dreadful performance. The database just sits there, idle, most of the time, waiting for the next command to arrive over the network. Network latency becomes the killer.
Right, because only one thing can happen at a time. If that one thing is waiting for the network.
It's done. Exactly.
And that's where stored procedures come in as like this elegant fix.
Precisely. Instead of all those network hops, the application packages up the entire transaction logic, all the selects, updates, inserts, the conditions, and sends it to the database in one go. As a stored procedure call.
One shot.
One shot. The database gets the whole recipe at once, runs it super fast, no more network waits, no disk I/O waits within the transaction. Think about booking that meeting room. Instead of select, wait, insert.
You just send one book room X if available procedure.
Exactly. And the database handles it all internally, super quick, totally sidestepping that network latency issue.
Okay, but stored procedures, they kind of have a bad rap sometimes, don't they?
They definitely do, historically. The cons often cited are things like vendor-specific languages, Oracle's PL/SQL, SQL Server's T-SQL, PostgreSQL's PLPG/SQL.
Right, kind of clunky sometimes.
Yeah, they can feel a bit old school, maybe less pleasant to work with than modern languages. And they were often hard to manage. Debugging could be a pain, version control wasn't always smooth, testing was tricky, plugging them into modern monitoring wasn't straightforward.
Okay, so some real downsides.
But the pros, especially with modern implementations, are pretty compelling. Look at VoltDB. It uses Java or Groovy. Datomic uses Java or Clojure. Redis uses Lua.
Ah, so general purpose languages. Much nicer.
Much nicer. And the performance gain from cutting out those network round trips and I/O waits can be huge. Plus, here's a cool production insight. VoltDB actually uses stored procedures for replication.
Oh, interesting. How does that work?
Well, it means the stored procedures have to be deterministic. They must produce the exact same result every single time they're run with the same inputs, no matter which replica runs them. That's how they guarantee consistency across the distributed system.
That makes sense. Determinism is key there. Okay, so how do you scale serial execution beyond just one really fast core?
Right. Partitioning, that's the next step. If you can design your system so transactions only need to touch data within a single partition.
Like all data for customer A is on server 1, all for customer D on server 2.
Exactly. Then each partition can have its own independent processing thread, running transactions serially just for that partition's data. Your overall throughput can then scale out really well, often, pretty linearly with the number of CPU cores you add.
Okay, that sounds great. Where's the catch?
The catch, and this is a huge red flag area for interviews, is cross-partition transactions.
Ah, when one transaction needs data from multiple partitions.
Bingo. Those require complex coordination between the partitions. They become vastly slower, and they impose a hard limit on your system's overall throughput. VoltDB, for instance, they report only handling about 1,000 cross-partition writes per second.
Only 1,000.
Yeah.
Compared to potentially millions within a partition.
Exactly. It's orders of magnitude slower. And critically, you can't just throw more machines at the problem to increase that cross-partition limit significantly. It really highlights how absolutely crucial careful data modeling is. You have to minimize those cross-partition operations if you want this architecture to scale.
Why? Okay, that's a major design constraint.
Yeah.
So summing up serial execution. It's awesome for small, fast, in-memory transactions, especially if you can partition effectively.
Right. Keep things local.
And you mentioned something called anti-caching.
Yeah, that's a neat pattern sometimes used. If a transaction tries to access data that isn't currently hot, isn't in memory, the database just aborts the transaction.
Aborts it?
Yeah. Then it fetches the needed cold data into memory asynchronously in the background. Once the data is loaded, the application just retries the original transaction, which should now find everything in memory and complete quickly. It avoids blocking the main thread on I/O.
Clever. Okay, so that's serial execution. Now let's shift gears. For about, 30 years before the serial execution rethink, the main way to get serializability was two-phase locking, right? 2PL.
That's right. For a long time, 2PL was pretty much the standard algorithm for serializability in databases. The reigning champ, as you said.
Okay, first things first. What's the #1 interview mistake people make here?
Ah, the classic gotcha. Confusing two-phase locking with two-phase commit.
2PL versus 2PC.
Exactly. They sound similar, trips up so many people. 2PL, two-phase locking, is about managing locks within a single database transaction to ensure correct concurrent execution. It's about isolation.
Okay, internal concurrency control.
Right. Two-phase commit, 2PC, is totally different. It's about coordinating distributed transactions across multiple separate systems, like multiple databases or microservices, to make sure they all commit or all abort together. Atomicity across systems.
Got it. Completely different problems. 2PL for concurrency, 2PC for distributed atomicity.
You got it. So let's break down 2PL mechanics. It basically uses two kinds of locks: shared locks and exclusive locks.
Shared and exclusive.
Shared locks are for reads. Multiple transactions can hold a shared lock on the same piece of data at the same time. Think of it like multiple people reading the same book simultaneously.
Makes sense.
Exclusive locks are for writes, updates, deletes, inserts. Only one transaction can hold an exclusive lock on a piece of data at any given time. If you want to write in the book, you need exclusive access.
Okay. And the key part for serializability.
The crucial interaction is this. In 2PL, writers block readers and readers block writers.
Unlike snapshot isolation.
Exactly. That's a key difference. In snapshot isolation, the mantra is often, readers never block writers, writers never block readers. But 2PL, it's stricter. If you want to read something, you might have to wait if someone else holds an exclusive write lock. If you want to write something, you have to wait if anyone else holds any lock, read or write.
And that blocking is how it prevents those nasty race conditions we started with.
Precisely. Take the lost update problem, two people incrementing a counter. Read 42, write 43, read 42, write 43, wrong.
Right. Only one increment actually counts.
With 2PL, the first transaction would get a lock, maybe shared to read, then exclusive to write. The second transaction would try to get a lock, see it's held, and wait. The first finishes, commits, releases the lock. Then the second one reads the new value, 43, increments it, and writes 44. Correct result.
Okay, so it serializes the access. What about write skew, the doctor's on-call example?
Same idea. Dr. A checks the count, needs a shared lock, sees two others. Dr. B checks the count, needs a shared lock, sees two others. Both think it's safe to go off call. Dr. A tries to update their status, needs an exclusive lock. Dr. B tries to update their status, needs an exclusive lock.
But they both hold shared locks from the read.
Well, or maybe one gets the exclusive lock first. The point is, the locks ensure that one transaction's check and update sequence completes fully before the other can even start its update, preventing the situation where both incorrectly decide they can leave. It forces one to see the result of the other's action.
Got it. So 2PL really provides that strong guarantee by being strict with locking.
Yeah.
Where do we see this used?
It's still quite common for serializable isolation. MySQL, specifically the InnoDB engine, uses it. SQL Server uses it. DB2 uses it for its repeatable read isolation level, which is strong, though not technically fully serializable on its own sometimes.
Okay, major databases.
Yeah.
Now, the two-phase part, what does that actually refer to?
Right. The name comes from how locks are managed during the transaction lifecycle. There are two distinct phases. Phase 1, acquiring locks. As the transaction executes its operations, reads, writes, it acquires all the necessary locks. It can only acquire locks during this phase. It never releases any. This is sometimes called the growing phase.
Okay, gather all the locks needed.
Then phase 2, releasing locks. This happens only after the transaction has finished its work and decided to either commit or abort. At that point, all the locks it acquired are released at once. It cannot acquire any new locks during this phase, sometimes called the shrinking phase.
Acquire,
Yeah.
then release everything at the end. Got it.
That hold locks until the very end strategy is the core of why 2PL works, but it's also the source of its main problems.
The performance issues.
Exactly. The big downside of 2PL and why it's not the default everywhere despite its guarantees is performance and predictability. First, there's just the overhead of acquiring and releasing all those locks. It's not free. But more significantly, concurrency is drastically reduced. Because readers block writers and vice versa, transactions spend more time waiting. If two transactions might conflict, one simply has to wait.
Leading to unpredictable delays.
Yeah, unpredictable and sometimes really unstable latencies. Especially at high percentiles like your P99 latency. A transaction might get unlucky and hit a lock held by a long-running transaction and just sit there waiting for ages. It makes performance spiky.
Not ideal for user experience.
Not at all. And then there's the other big headache, deadlocks.
Ah, yes, the deadly embrace.
The classic. Transaction A gets a lock on resource X, then tries to get a lock on resource Y, but transaction B already has the lock on Y and is now trying to get the lock on X.
They're stuck waiting for each other.
Yeah.
Forever.
Exactly. Circular dependency. Now, databases using 2PL are smart enough to detect these deadlocks automatically. But when one is detected, the only way to resolve it is to
Kill one of the transactions.
Yep. One transaction gets aborted, its work is rolled back, and its locks are released so the other can proceed. The application then usually has to retry the aborted transaction.
Which means wasted work and even more latency for that user.
Precisely. I remember chasing a deadlock once. Oh man, it only happened during peak holiday sales, maybe once every few hours. Finding the exact sequence of locks that caused it under heavy load. It was like trying to untangle, a massive ball of yarn after the cat's been playing with it all night.
Oh, great analogy. Brings it home. And that leads perfectly to another interview question, right? What are the common issues with two-phase locking, and how do you handle deadlocks in production?
Absolutely. You need to talk about the performance impact, the latency spikes, and for deadlocks, the key is usually robust retry logic in the application, maybe exponential backoff. Sometimes, if you can, you try to make transactions always acquire locks in the same order to prevent cycles, but that's often hard to enforce.
Good tips. Okay, one more tricky thing with 2PL phantoms.
Yeah.
How does it prevent those? Because it seems like locks are on existing rows.
That's a sharp point. Phantoms are tricky. Remember, a phantom is when a row appears or disappears that matches your query after you've already run the query but before your transaction finishes. Like the meeting room booking example. You check for bookings between noon and 1 p.m., see none, then try to insert yours. But someone else inserts a booking in that exact slot right before your insert goes through.
Right, the double booking. Your initial select was made invalid by a concurrent insert.
Exactly. So how do you lock something that doesn't exist yet? You can't put a row lock on a row that isn't there.
Yeah.
The theoretical answer is something called a predicate lock.
Predicate lock.
Yeah. Instead of locking a specific row, you lock the condition, the predicate, from your where clause. So you'd lock conceptually all rows where roomid equals 123 Andy booking time is between noon and 1 p.m. on January 1st, 2024.
Locking the query condition itself.
Right. This lock would then prevent any other transaction from inserting, updating, or deleting any row that would match that predicate, even if no such rows currently exist. It's the perfect theoretical way to stop phantoms.
Okay, that makes sense conceptually. So back to the interview. How do you prevent phantom reads in a booking system? What's the practical answer?
Right, because while predicate locks are the perfect theory, they have a huge problem. They perform terribly.
Right.
Imagine having hundreds of active transactions, each with potentially complex predicate locks. For any write operation, the database would have to check if the row being written matches any of those active predicate locks. That's computationally very expensive. So using actual predicate locks is generally an anti-pattern for performance.
Okay, so theory good, practice bad. What do databases do instead?
The practical approximation, the thing most databases using 2PL actually implement, is called index range locks, sometimes also called next key locking.
Index range locks, okay.
Instead of locking the abstract predicate, they leverage the database indexes. If your query is filtering on an indexed column, say roomid and booking time, the database can lock the relevant entries in that index, or maybe a range of index entries that cover your query.
So it locks part of the index structure.
Exactly. By locking the index entries corresponding to room 123 noon to 1 p.m., it effectively prevents any other transaction from inserting a new row that would need to modify that part of the index. It blocks conflicting writes or inserts based on the index. It's less precise than a true predicate lock, maybe, but it's way, way faster to check.
Much more performant. Got it. And what if there isn't a good index? What's the fallback?
If there's no suitable index to place a range lock on, the database often has to escalate the lock. To be safe and guarantee serializability, it might have to take out a lock on the entire table.
Whoa, lock the whole table.
Yeah. Obviously, that's terrible for concurrency. It stops all other writes to that table, but it's the safe fallback to prevent phantoms if index range locking isn't possible. It's called lock escalation. You definitely want to avoid it with good indexing.
Definitely. Okay, this is super helpful.
Good. Let's maybe switch gears slightly and put some of this into practice. How about a few quick-fire interview scenarios?
Yeah, let's do it. Hit me.
Okay. Scenario 1. You're designing an e-commerce inventory system. Very high concurrency. How do you prevent overselling the very last item when potentially hundreds of customers try to buy it at the exact same moment?
Right. Okay, classic race condition. That's the lost update problem on the inventory count. First thing, for absolute correctness, especially with inventory, you probably want serializable isolation. That guarantees no overselling.
Okay. How do you achieve that?
Well, using the methods we discussed, if I use two-phase locking, 2PL, locking that specific item's inventory record would work. But if it's a super hot item, that lock could become a massive bottleneck. Lots of contention, maybe deadlocks, transactions failing, needing retries, could be slow.
Right, the hotspot problem.
Yeah. The alternative is actual serial execution. If the active inventory data fits in RAM and the decrement inventory transaction is really fast, maybe running it single-threaded for that item or partition could actually be faster by avoiding lock contention.
Yeah.
But you're limited by that single core speed.
Good trade-off analysis. What else?
Crucially, I'd ask clarifying questions. What is the scale? How many concurrent buyers are we really expecting for one item? What's the acceptable latency for a purchase confirmation? Importantly, what's the business tolerance for any overselling? Is near perfect okay, or does it have to be absolutely zero? That guides the choice.
Excellent. Identifying the core problem, discussing alternatives with trade-offs, and asking clarifying questions. Perfect. Okay, next one. How does partitioning affect serializable isolation, especially if a transaction needs data across multiple partitions?
Okay, partitioning and serializability. So if transactions stay within a single partition, generally great. Each partition can process its transactions serially and independently, so you can scale throughput pretty well, often linearly with CPU cores.
Right, the happy path.
The happy path. But the moment you have a cross-partition transaction, things get way harder and slower. It requires complex coordination protocols, like maybe two-phase commit, 2PC underneath, to ensure atomicity and isolation across partitions. Throughput drops dramatically. We talked about the VoltDB example. Maybe only 1,000 cross-partition writes per second, a hard limit.
And the implication for design.
Data monitoring becomes absolutely critical. You have to design your data layout and transactions to minimize the need for cross-partition operations whenever possible. Keep transactions local. That's key to making partition serializable system scale.
Spot on. Recognizing that cliff in performance is crucial. Okay, last one. Why might stored procedures be controversial in modern system design, but when would you still argue for using them?
Stored procedures.
Okay.
Got the controversy. I'd first acknowledge the history. They got a bad reputation, right?
Yeah.
Often tied to vendor-specific kind of clunky languages like PL/SQL or T-SQL. They could be difficult to debug, hard to version control properly, tricky to test, and didn't always integrate well with modern dev workflows and monitoring. The developer experience wasn't always great.
Right, the historical baggage.
Exactly. But then I'd pivot. Modern implementations often use standard general-purpose languages, Java, Groovy, Clojure, Lua, like we mentioned. That makes them much more palatable. And I absolutely advocate for them in specific contexts, particularly high-performance, latency-sensitive OLTP systems that might be using that single-threaded serial execution model.
Why specifically there?
Because in that model, eliminating network round-trip latency is paramount. Sending the entire transaction logic in one go via a stored procedure gives a massive performance boost compared to interactive transactions, especially if the operations need to be deterministic, which also helps with things like replication consistency. So it's not a simple good or bad. It's about the specific trade-offs in that context.
Perfect. Showing that nuanced understanding beyond just the historical view is exactly what interviewers look for.
Phew. Okay, that's a good workout. So pulling this all together, what does this mean for you, the engineer, prepping for that senior interview? And we've really dug into this world of transaction serializability, from that gold standard promise to the actual nuts and bolts of how databases like VoltDB or MySQL achieve it using serial execution or two-phase locking, and crucially, how it prevents those really sneaky race conditions.
Yeah, and the core tension, the thing you'll always be wrestling with in distributed systems, is that fundamental trade-off. You want absolute correctness, that perfect serializability, but you also need performance and scalability. They often pull in opposite directions.
Sure.
We saw how serial execution gives you perfect isolation, but it has specific constraints, especially around in-memory data and partitioning. And 2PL gives strong guarantees, but at the cost of lock contention, unpredictable latency, and those pesky deadlocks.
And understanding those specific race conditions, lost updates, right skew, and especially phantoms is so important. Knowing they exist isn't enough. Knowing the practical solutions databases use, like index range locks instead of theoretical predicate locks, that's what really makes you stand out in a system design discussion.
Absolutely. And maybe here's a final thought to leave you with. Just consider how these fundamental ideas, locking, serial execution, dealing with concurrency concepts developed decades ago, are still so incredibly relevant and foundational, even in the most modern, distributed in-memory systems being built today.
Yeah.
The core principles of concurrency control, they're truly timeless. They continue to shape how we build reliable, scalable software.
That's a great point. The fundamentals endure.
Yeah.
So if this deep dive helped untangle some of these complex ideas for you, maybe gave you a bit more confidence for that next tech interview,
We hope so.
please do give us a like and definitely hit that subscribe button so you don't miss our next one. And seriously, leave us a comment. Tell us about your own nightmare race condition stories, or maybe which isolation level you find most intriguing or useful. We genuinely love hearing from you all.